Right. So one thing I want to make you aware of when I was looking at um, the rest of the semester on schedule and so forth, and how much time was allocated for each thing, et cetera, I thought I needed to make some changes to the schedule, and I updated that here in Canvas. And what that means is, well, because for the section about to cover convergence analysis, I had originally budgeted 3 class periods, and it turns out I only have notes for 2. The 2 class periods all takes. I had a section here that I'd assigned myself to cover, and I'm not sure why I did that, because I didn't have notes for it, and it doesn't affect anything else, so I'm not going to. So, well, 6 I removed. So the upshot of all this is this is where it ends. Well, April 22nd, so 3 weeks from last Monday, is the last day I actually cover stuff. Now, for those of you who choose the coding option for the final project, so the next class period, April 24th, is for that. But if all 5 of you end up doing the oral one, then you won't have that either. So then the last official week of classes, which is April 29th, May 1st, we do not meet.
And all our students are due on April 20th?
What?
What day was all our students?
So last week of classes is for Monday, April 29th, and Wednesday, May 1st. So we won't meet, but classes will.
Well, I meant like when we do all our stuff turned in.
Okay. Well, yeah, that I announced before. Where the Thursday of finals week, which is May 9th, is when I like everything in, because let's see. Yeah, because grades have to be turned in to SOAR May 13th. So having it on the 9th, that's enough time to read all your stuff, especially since there's only 5 of you. Big stuff at me, yeah. Well, not too many things because there are only 5 of you. Okay, so this is what we got for the rest of the semester. So convergence analysis. Then last 4 class periods of covering stuff is value problems or ODEs. Coding option for final is entirely based on that. Okay, just so you know what's what. So with that in mind, it's time for convergence analysis. So when I first started covering typesetting methods for ODEs, looked at the Euler's method, and I showed you how to prove that as time step h goes to 0, that this error, which is defined to be the difference between the computed solution at time tn minus the exact solution at time tn across all time steps, however many you have, to get from your initial time t0 to your final time capital T, that all these errors goes to 0. Now, even though Euler's method is a really, really simple time stepping method, that proof was a bit of a pain. So the idea here is to establish a general framework for proving that more elaborate methods, higher order 1-step methods, also multi-step methods, converge. So I'm actually going to introduce a few concepts. So I'll give some general definitions of them first, and then I'm trying to redundant today. So after giving some general definitions, I will show how those concepts are analyzed when it comes to 1-step methods and multi-step methods, because the methods are different enough that the specifics for the 2 categories of methods are quite different. Okay. So the first concept that we need to determine whether a method converges is called local truncation error. So local truncation error is a measure of how much error is occurring during one time step. Whereas this is the error we actually care about. This is the error we need to show goes to 0. But when you're at time tn, there's error occurred from all time steps from first one up to n. And that's not easy to analyze. But here, what is easier to analyze is, and still useful to us, is what happens during the single time step. And the way you determine that is you take the, so this is the important part right here. You take the exact solution of your problem, your ODE, and you substitute it into the numerical method. So when you substitute the exact solution of an ODE into the ODE, of course it's satisfied. That's what it means to be a solution. The numerical solution exactly satisfies the method that produced it. Okay. So because the numerical method is based on an approximation of the ODE, when you substitute the exact solution into it, it's not going to satisfy it exactly. There's going to be something left over. And that is, so whatever we get that's left over, after dividing by h, that's really a convention thing, but it's definitely the best way to go. Then whatever's left over after dividing by h, we call the local truncation error. So I'll just illustrate local truncation error with Euler's method. So, so what I do is, we see here, I've rewritten Euler's method so that everything is moved on to one side, set equal to 0, and then divided by h. And that leads me to this expression right here. So this is what you get if you move all of Euler's method to the left side, substitute the exact solution y of t into the method. So for instance, yn plus 1, that's the computed solution at time tn plus 1, is replaced by y of tn plus 1. That refers to the exact solution. Same thing over here, f of tn, and then yn is replaced by y of tn. And then we divide by h. Now, here you can get an idea as to why it makes sense to divide by h, because this difference quotient here, because I've divided by h, what is this an approximation of?
Derivative.
Yes, y prime of tn. So I have y prime of tn minus f of tn, y of tn. So if this was the exact derivative, instead of this difference quotient, then all this would be 0. But because there's an approximation here, we're going to have something, and that something is labeled tau n. So tau is the letter that's conventionally used for local truncation error. So this is how the local truncation error is by definition. But this expression is not particularly useful to us. It doesn't really help us quantify how large it would be. So what we do is we use Taylor expansion of a y of tn plus 1 around tn. And after simplifying as much as possible and keeping in mind that y of t is the exact solution, so y prime of tn equals f of t and y of tn. So this term will cancel with this one, and after dividing by h and all that, this is what you're left with. It's h over 2 times the second derivative at an unknown point. That's between tn and tn plus 1. And we say that this is big O of h because this local truncation error is proportional to h. So in other words, first order accurate. Yes.
How would you perform convergence analysis if you don't have an exact?
Well, this analysis, you never actually work with like a formula of the exact solution. You're using the fact that it satisfies the original.
So it's all theoretical.
All theoretical. Yeah. I mean, if you have a problem, a specific problem for which you do know the exact solution, you can use that to try to illustrate or corroborate the theory, but yeah. So now this leads to a concept that's basically adjacent to convergence. Consistency. So we say that a method is consistent if the local truncation error goes to 0 as h goes to 0. Now, what we really want is to show a method is convergent. That this error goes to 0 as h goes to 0. So this alone is not everything, but it is a key step. Now, another concept that we need that's on the way to convergence is stability. Well, a method is stable if making a small change in the initial data does not lead to an unduly large change in the solution. So if you change the initial data for your problem a little bit, if you can prove that the change in the solution over a whole time interval, from initial time to final time, can be bounded in a way that is independent of h, then the method is stable. And what we'll see is, I don't know if I'll get to it today, but it's for next time, that if you have a method that is consistent and stable, then the method can prove to be convergent.
Is it by any chance like LAX?
The lax code. Yeah. So the actual lexical theorem might apply to something more specific, but yeah, there are a lot of cases for typesetting or for ODEs or PDEs where you have this universal truth that consistency plus stability equals convergence, and often is an if and only if kind of thing. And actually, at some point during this section, for one-step methods in particular, I will be able to prove that at least in one direction, that you have consistency and stability, you do have convergence. So, what I'm going to focus on now is how do you show consistency for one-step methods and multi-step methods, and also how do you determine the order of accuracy? Because the consistency is just, okay, the local truncation error goes to 0 as h goes to 0. But we also are interested in the order of accuracy. At what rate does the local truncation error go to 0? It goes to 0. Is it they go h like for Euler's method, or is it a higher power? Now, the way that any one-step method can be described using this framework here, which is kind of similar to Euler's method. The y plus 1 equals yn plus h times some function, so it's a capital phi, of tn, yn, and h. So in the simplest case, Euler's method, your function capital phi just turns out to be f. But for something like RK4, it's going to be a lot more elaborate than that. So then the way you describe the local truncation error is very similar to what you see here for Euler's method. So it's your difference quotient for your time derivative minus phi, where the exact solution is plugged in for the y parameter. And then suppose we let h go to 0. Well, then this difference quotient converts to y prime of Tn. Now, we want this to go to 0 as h goes to 0. So y prime of Tn has to equal f of Tn y Tn. So, and here, because h is going to 0, the third argument of capital phi, it becomes 0. So if this expression, the limit as h goes to 0, is equal to f of Tn y Tn, we're good. That we have consistency. The local truncation error really is going to 0 as h goes to 0. So this is how you tell if a one-step method is consistent. You get your function phi, and then you plug in h equals 0, that argument. And if the whole thing reduces to f, the method is consistent. Now, that doesn't tell you the order of accuracy. More work is needed for that, like Taylor expansion. But at least we have a simple way of checking for consistency. Now, I'm going to do a couple examples of this, how you get 5, but I want to point out an intentional discrepancy between what you see here in notes versus the book. So in the book, I describe my general framework for one-step methods a little differently, where I have the function of Tn, Yn plus 1, and h. So one thing that bothered me when I was writing the book was, when I've seen other textbooks on numerical analysis and scientific methods, they have the same kind of framework for one-step methods, and it's this one right here. So you have Yn, but you don't have Yn plus 1. And that bothered me. It was like, why don't they include that? Like, how are you supposed to describe an implicit method, which depends on Y plus 1? So I added it. But then I thought, like, well, there's so many authors are doing it the other way. Like, what am I missing here? Then I realized that you don't really need to include it as long as you're okay with defining phi in an implicit manner, like a recursive manner. And I will show you an example of that. And it makes sense because for an implicit method, Y plus 1 is an implicit function of everything else. So you have this equation to solve like by iteration. So Y plus 1 is described in a self-referential manner. So it only makes sense that phi for an implicit method is also described in a self-referential manner. It's kind of weird, but we're going with it. So I'm trying to be consistent with the community here. And then the next edition of the book will definitely have that. So that's what I've done throughout the notes. In case you go look at the book and see a discrepancy. And it does simplify a lot of things. So here's some examples. First, for an explicit method. Okay, so here's the midpoint method, where what you do is you evaluate the time derivative at the midpoint of the interval in time. So Tn plus half a time step. And then for y argument, you use Euler's method to approximate the solution at this midpoint in time. So in this case, your function phi is it's whatever's multiplying the h. So it's just this evaluation of f with these arguments. So then I go ahead and set h equal to 0 throughout this, and this term goes away, this term goes away, and you're left with f of t n y n. So it's consistent. This doesn't reveal to us that it's technical or accurate, but I'll go around that later. Now, as for an implicit method, that's a little trickier. So trapezoidal method. So here's the actual method where we evaluate f at t n y n, and then again at t n plus 1 and y n plus 1. So your phi function in this case is, okay, so 1/2 f of t n y n. And then here, where you have y n plus 1, I've just replaced it by the general framework. So because yn plus 1 is always yn plus h times phi. So it's a bit clumsy, but it works. And it certainly works for showing consistency, because then I go ahead and set h equal to 0. So this term goes away, and this term goes away. So I end up once again with f of t and yn, and you have consistency. So whatever framework you use, everything works out. Now, so what about order of accuracy? Oh, okay. I don't have it written here in notes, but I do have an example that I can show you. Like I said earlier, Taylor expansion on a local truncation error once you have it. So I'll show you how it's done for the midpoint method. Okay, this is where it's shown consistent. Okay, so what we do here, so this is the midpoint method with the exact solution substituted in for y and divided by h, so that's local truncation error. Again, useful expression for local truncation error. What you do is you Taylor expand your solution around time Tn, and a multivariable Taylor expansion of your phi around Tn in time and y of Tn for the y value. So there's two Taylor expansions happening here. So here we Taylor expand y of Tn plus 1 around center Tn, and this is what we get, and we take it out to be past the second derivative term. And then for the f part, here's where we do multivariable Taylor expansion. So here we have, oh, I think I missed a parenthesis there. Yeah, I did. So for the t portion, we have the increment in t is just h over 2 times df dt, plus the increment in y, which is h over 2f, times df dy, so that's all that right here. In this case, for multivariable Taylor expansion, we only take it through the first derivative terms. It turns out we won't need anything beyond that. So everything that I've left out is order h squared. So then, this second derivative term, y double prime, keep in mind that y prime is f of ty. So for second derivative, I did the same chain rule usage when deriving Rogan Cohen method. So y double prime is df dt plus df dy dy dt, which is f. So y double prime of Tn is equal to this. But then we have cancellation between these terms here involving the partial derivatives of f with respect to t and y, and these terms down here that come from the multivariable Taylor expansion of f. So, so this cancels with this. Actually, yeah, everything you see written out here cancels. And in the fraction, we have order h cubed up top, but it's divided by h, so that's order h squared. And then you have order h squared for multivariable Taylor expansion. So everything that's left after you cancel whatever you can turns out to be big O of h squared. This is not a precise error formula. For that, it would be better to take the Taylor expansions out just a little bit further. But it's still enough to show that the local truncation error is proportional to h squared. So this method is second order accurate. So in general, you have your framework for your one-step method. You determine your function phi. You multivariable Taylor expand phi, and you Taylor expand y of tn plus 1. And then between those two Taylor expansions, cancel whatever you can. And voila, that's your order of accuracy. Up to it. So questions about how order of accuracy was determined in this case? Okay. That's one-step methods for consistency. Now, what about multi-step methods? So here we have a general multi-step method, whether it's atoms or BDF or anything else. So then, the way you define local truncation error, same way as for one-step methods. You move everything on one side, on the left side, and you substitute the exact solution into the method. So here we have y at time level n plus 1 minus I. That's the same as replace with y of t sub n plus 1 minus I. And then we do the same kind of substitution over here. Okay. Here there's this normalization here to divide by the sum of the betas usually the betas are described, so certainly true Adams method, that the sum of the betas is equal to 1 anyway. But in case your method is written differently, it's best to normalize it this way. So for Adams methods, the sum of all betas is 1 by convention. So this is what you get. So this is kind of similar to what we saw for local truncation error for one-step methods. You have the same fraction over here, we just have a more complicated expression over here. But then if we keep in mind how the betas for Adams methods were described, remember that this part here, y at t plus 1 minus y at tn, is from the integral form of the ODE is this integral. So really, our local truncation error is 1 over h times the exact integral minus this sum, and this sum is meant to be a quadrature rule. So here we're replacing the exact integral in our Adams method by the exact integral of this polynomial that interpolates f at these times. So what happens for the explicit case is you have 1 over h times the integral, times the quadrature error. So it's the integral of the error that you get from polynomial interpolation. Because what we have here, what an Adams method does, and you saw this when, for example, I derived the Adams-Bashforth method last class, the beta i's are quadrature weights for interpolatory quadrature. Recall from last semester, the interpolatory quadrature, this is from early chapter 9, that the exact integral of some function f is approximated by the exact integral of a polynomial that interpolates f at select points. Okay. Now, when you have interpolatory quadrature, the way I like to describe it concisely is the error in the integral is the integral of the error. And the latter error in this case is the error in polynomial interpolation. So this integrand right here is literally the polynomial interpolation error. So this is a theorem in the book where that error formula is given. That comes from interpolating f by these values at these times. Actually, we get a little clearer. It is s equal to all of these values. So now we have a more useful expression for local truncation error. Because then what we can do is use what's called the weighted mean value theorem for integrals. Because what I can do is I can make a this expression here never changes sign because s goes from tn to tn plus 1. Here we have time tn and earlier times. So all of these factors are non-negative. This is for the explicit case. For the implicit case, there's a factor of s minus tn plus 1. But that factor is always going to be non-positive. The point is, for explicit or implicit, this product of linear factors you have here never changes sign. So when you have what the weighted mean value theorem for integrals allows you to do is you can state that an integral like this, that's a product of two functions, so this one here, is equal to one of the functions you pull out, in this case the f, evaluated at an unknown point that's between your limits of integration. And you're allowed to pull it out as long as whatever remains in your integrand does not change sign on the interval of integration, which is true in this case. So what ends up happening is this local truncation error can be expressed this way, where this integral is simplified from, I make a u substitution. So Here I have this integral with respect to s. I make this u substitution. That same one I showed you last time that maps your interval in time to 0, 1. And now this integral can be evaluated so that we actually get a specific constant here. All right. So, okay. Okay. Here, what I have is for a general multi-step method, so beyond atoms. What's happened in this case is I take this general expression for multi-step method with the this multiplication error, and I do the same kind of Taylor expansion as I showed you for the midpoint method to show the second order accurate. I Taylor expand my solution values around time tn plus 1, so that's a slight difference. And then multivariable Taylor expand these around the corresponding center. And what happens after a lot of calculus and algebra is you end up with this expression here for local truncation error. And you have these constants, the C0, C1, C2, etc., that are defined right here in terms of the coefficients of your multi-step method, your alphas and your betas. So you end up being able to determine the order of accuracy of your multi-step method by determining how many of these capital C constants are equal to 0. Because each one of these C's is multiplied, like CK is multiplied by H to the K. So if all these coefficients, C0, C1, C2, up to CP, are all equal to 0, and the next one, CP plus 1, is non-zero, then the order of accuracy is P. So the error is proportional to H to the P, because let's suppose that all of these are 0, all these C's are 0, up to until CP plus 1. That's multiplied by H to the P plus 1. So we have an H in the denominator down here. So the local truncation error is big O of H to the P. So for any multi-step method, atoms, BDF, whatever, or neither, you can always use this. And so then we have this formula for local truncation error, although I should mention that there's a slight mistake in it. It should be minus H to the P plus 1. Oops. And that mistake is noted in the notes. And so this CP plus 1, that's something that can be figured out, that it comes from your from your coefficients. Or for the case of an Adams method, you get your constant by evaluating this integral. That works out the same way. So that's how you can show that, for instance, that Adams methods, like Adams Bachelor methods, are M4 accurate, or M's number of steps, or Adams Moulton is M plus first order accurate, and so on. Okay. So, put some examples here. I thought I did. Oh. No, I don't. But like, if you look up, for instance, Adams methods, like in Wikipedia, for instance, it probably has the values of these constants for different numbers of steps. So you can like check those values against what you would get from here. So questions about local truncation error for multi-step methods, particularly Adams methods. weighted mean value theorem for integrals is probably one of the most useful theorems for calculus in all numerical analysis. So many things seem to come from it, like proving formulas about interpolation error, or well, actually, it's helpful for even proving Taylor's theorem itself. This seems to come up a lot, and I'm not sure if Cal 2 instructors might even gloss over it. I mean, everyone covers the mean value theorem for derivatives in Cal 1. I'm not sure if even mentioned the mean value theorem for integrals at all, let alone the weighted one. So, okay, yeah. So that's the story on consistency, one step versus multi-step. So you see that there's a same starting point, you substitute the exact solution into the method, but then, using the same tools like Taylor expansion to show order of accuracy. Okay. Stability, I think I only have in my notes for today, okay, for one-step methods. And then I'll get the stability for multi-step methods on Monday. Now, the concept of stability for a numerical method is related to the concept of well-posedness for the underlying differential equation. So we say that an ODE, a general ODE, is so well-posed if the solution exists, the solution is unique, and if the solution depends continuously on the data. So a small change in the problem data would not cause a large change in the solution. And that's true if the function f, your time derivative, is Lipschitz continuous in the y variable. So if I evaluate f at the same t value with different y values, but the difference between these f values is bounded by a constant called the Lipschitz constant times the difference in the y values. If f is differentiable with respect to y, that's the same thing as saying is that the partial of f with respect to y is bounded by L. That comes from the regular mean value theorem for derivatives. So it was a similar notion of stability for similar way of finding stability for a one-step method. So here we have a general one-step method. So if it is satisfied the Lipschitz continuous, if your phi function that defines your one-step method is Lipschitz continuous, also in the y variable, just like f is Lipschitz continuous in the y variable. Okay. So let's suppose we have two different initial values, same ODE. Then, if we apply our one-step method for both cases, both sets of initial data, and then we subtract, then this is what we get, that the difference in your solution at time tn plus 1 is less than or equal to the difference at time tn plus h times the difference in these phi values. But if phi is Lipschitz continuous in the y variable, then this difference is bounded by a Lipschitz constant times the difference in those y values. So now I can substitute this upper bound for this expression here. So now I have the difference in my solution values is less than or equal to 1 plus HL times the difference in previous solution values. But then what I do is here we have this recursive relationship, how each error relates to the previous error. So now I apply this repeatedly. So now the difference in computed solutions at time tn is less than or equal to this factor times the difference in your initial values. But this right here is bounded by this exponential. And because h times n is equal to the difference between your final time and your initial time, I have here that the difference in solution at time tn is less than or equal to this factor that, notice, it is independent of h times the difference in your initial value. So a small change in your initial value causes a bounded change in your solution for your entire time. And I want to mention where this constant capital K is coming from. if I look at, if I scroll back to the general definition of stability, yeah, right here, that that for all time steps, the difference in your computed values is bounded by some constant k that's independent of h, that's very important, times the difference in your initial values. So here, in this case, for this one-step method, because we have Lipschitz continuity of phi, if we have that, then we can actually say what the constant capital K is. Okay. So in other words, showing that your function phi that defines your one-step method is Lipschitz continuous to y argument, that is a sufficient condition for the method being stable. So now we have, for one-step methods, we have a simple way to check if the method is consistent. You set h equals 0 in your phi function to make sure you get f. We have a less simple way of showing it's stable by showing that it's a Lipschitz continuous in the y variable. In other words, coming up with Lipschitz constant. And from these manipulations here, show that once that has been accomplished, we actually do have stability in the sense of the original general definition that applies to all time steady methods. So questions about how the Lipschitz continuity leads to stability. I'll show an example, show that the midpoint method is stable. So here's the midpoint method. So if I take what's multiplying h, that's this evaluation of f here, I need to show that this function, and I've stripped out the subscripts just to reduce clutter, that this function is Lipschitz continuous in y. Now we're going to assume that f is Lipschitz continuous. That's a reasonable assumption. We often assume that your time derivative has Lipschitz continuity in the y variable, just to, because that's what the is the assumption for the existence of the equal pair. So we're assuming we have a well-posed problem. So we use x Lipschitz constant of L. So the difference in phi values, notice that t values are the same, h values are the same, but y values are different. So then we fill in what phi is, evaluating f. And then we use the fact that f is Lipschitz continuous. Then we have, so this difference is bounded by L, x Lipschitz constant, times the difference in the y argument. So here I have this y argument minus this y argument. And whoops, that should be a minus here. Then triangle equality, I have L times the difference in y values. Then I have plus HL over 2, difference in f values. But then I use the Lipschitz continuity of f again to, so then I have an additional factor of L, so L squared. So now I have this expression in large parentheses is the Lipschitz constant for phi. So I use an L sub phi is Lipschitz constant for phi to avoid confusion with the plain L, which is Lipschitz constant for f. As long as it can be bounded as h goes to 0. So because that's what we care about. We want to see what happens as h goes to 0. So if I assume that h is less or equal to some value h naught, this Lipschitz constant is so this Lipschitz constant applies for all h for they're down to 0. And so now I have enough to conclude immediately based on the analysis conducted up here that the midpoint method is stable. So if we know a Lipschitz constant that is But basically, it's bounded independently of H for H sufficiently small. And then you go. Okay. That's as far as notes go today. So what I'll do is on Monday, I'll pick up with how you show stability for multi-step methods, which is very different. Actually, it's simpler. And then how we use consistency and stability together to show convergence. And then also talk about what it means for ODEs to be stiff and the difficulties that that poses. Do we have questions about anything? Do we ever?
Homework. I have homework.
You do? Okay.
But I don't know how to say that. I just want to show it to you.
Okay. It's okay. Well, anyone else who doesn't have any questions, they can scram.